Okay, first of all, I'd like to thank organizers for giving me opportunity to talk in the in-house. Uh, I will be talking about dynamics of eigenvalues for a correlation matrix in some free fermionic systems, which have point defects. It's a small part of a couple of works that I have been doing, one with Manas and Bijay, who is a faculty in ICER Pune. This paper just got published last week. And another work with Manas, Madhumita, Abhishek, David Hughes, which is still in preparation. Okay. So we'll be considering uh, such kind of setups where we have a 1D free fermionic chain, which is divided into two parts. One, which is a finite part, and another, which is an infinite part, and which have some hopping, which is given by G. And these two subsystems are coupled by a defect. Now, this defect can have various kind of terms in the Hamiltonian depending on what kind of defects you are dealing with. But okay, yeah, and we will also consider an initial condition where this first finite subsystem is completely filled and the reservoir is initially completely empty. And then we'll evolve it using this Hamiltonian and we'll see what happens. Okay, just a side note before getting to the main part. In such system, we can always solve a kind of a scattering problem where you have some incoming wave function, which because of the defect, which acts like some kind of a barrier, a potential barrier, the wave function transmits a small part gets reflected with some probability, reflection and transmission probability. Here we will be denoting reflection probability by R of k and transmission probability by T of k, where this subscript k just denotes the momentum of the incoming wave. Okay, and I'll specifically talk about a kind of defect which is called conformal defect, which is just given by like a different hopping at the defect site with some on-site potential. The exact structure of the defect is not important, but the important part is in the scattering problem, the reflection and transmission coefficients are independent of the momentum of the incoming wave. And as you can see here, the reflection coefficient just depends on the ratios of the two hopping constants, 1 minus gc by g the whole square. Yeah. And now let's get to the main part, which is how the eigenvalues of the correlation matrix evolve. The correlation matrix is given by the I comma jth element of the correlation matrix is just given by the expectation value of C dagger I Cj at any given time. And since we are dealing with a non-interacting system, the correlation matrix has all the information regarding such systems, especially if we are talking about, say, entanglement between, say, two subsystems of the setup, the eigenvalues of correlation matrix have those information. The eigenvalues also have some information regarding the full counting statistics, and hence knowing how these eigenvalues evolves can give us a lot of idea about how the entanglement itself evolves. So we'll consider the correlation matrix, and especially we'll consider two blocks of this correlation matrix. The first LS cross LS block, which is I'll call system part, and then LR cross LR block, which is this reservoir part. This contains the correlations of the system. This contains correlations of the reservoir. And I'll individually diagonalize each of this block. And diagonalize the blocks, and I'll consider the eigenvalues of those blocks. Now, okay, now comes the interesting part. So what I did was I just took the eigenvalues of those two parts, for the system part, the reservoir part, and I just plotted them in the descending order of their values. And since I'm considering a domain one initial condition where the system is full, initially all the eigenvalues in the system part are 1, all the eigenvalues in the reservoir part are 0. And I'm considering a system of size 160. So that's why there are 160 eigenvalues. Okay, now let's see what happens when I just evolve this setup. Now, as you can see, when I evolve this setup, the eigenvalues go from 1 to some constant value. Like they just drop to some constant value. And as it turns out, this constant value is nothing but the reflection coefficient of the setup that we mentioned before. And similarly for the reservoir part, since it's a unitary dynamics and the trace needs to be conserved, the eigenvalues go from 0 to 1 minus Rk. Now suppose we further evolve this setup. Let's see what happens. The eigenvalues which were at Rk level go from Rk to Rk square at time t is equals to 2 times the system size. Now if I evolve it further, the eigenvalue go from Rk square to Rk cube at 4 times the system, time equal to 4 times the system size, and so on. Like at time t equals to 2 and times ls, the eigenvalues drop from Rk to the power n to Rk to the power n plus 1. And accordingly, it happens in the reservoir part. So you can see that like the eigenvalues which contain some information of the entanglement are somehow related to the transport that is happening in the system, because this Rk square reflection coefficient, they are related to transport. Now to exactly understand what is happening, we can consider a heuristic picture. This is not the exact picture that is what is happening, but it gives some idea, some physical understanding of what exactly is happening with these eigenvalues. So what we will do is we will consider the same setup, but in that we will consider some single particle wave functions phi, which will have some initial position and some initial momentum. And we'll define a new kind of correlation matrix, where the elements of correlation matrix C bar are just some product of the wave functions with different initial condition, and I'm just summing them over the system part. Just note that if I just sum over system and the reservoir completely, I'll just get a delta function. So, yeah. And I'll just assume that the overlap between two different wave functions is negligible. And in assuming so, what happens is that this correlation matrix just becomes a diagonal matrix. And as we know that for a diagonal matrix, the eigenvalues of eigenvalues of the matrix are nothing but the diagonal elements. So the eigenvalues can be approximated as the sum over the system part of the probability of the wave function. So we'll just consider a Gaussian wave function, a Gaussian wave packet. So the setup that we had, I considered like say 10 Gaussian wave packets with random initial conditions x0, k0. Here I'm plotting the probability distribution of one of the wave packets, and I'll evolve that. And here I'm plotting the diagonal elements of the correlation matrix, which are just sum of this probability distribution over the system part. And just see what happens with this the value which is marked by red. This corresponds to the diagonal elements of this wave packet. Just see what happens. Initially, it has some position. When I evolve the setup, you will see this wave packet, it moves towards the right, hits the defect, a part of it gets transmitted to the reservoir, and a part gets reflected to the system. And again, it moves toward the left, it will hit the finite wall, and then again move toward the right, and it will repeat the process. But see, whenever it hits this finite defect, this eigenvalue, it jumps from some Rk to the power n to Rk to the power n plus 1. So it turns out the eigenvalues, the values that these eigenvalues are taking is related to how the particles in the setup is going from system to the reservoir. So you can see that there is a very close and direct relationship between how the eigenvalues, which contains the information of the entanglement between these two subsystems, is related to the transport in such systems. Yeah. So what do I do with this kind of simulations? Like, what will I do with this information? This, even though it is interesting, like, what can I do? One thing that we can do is determine the some functional form of the entanglement dynamics, at least up to the leading order. Like, for example, for the conformal defect case, we've been able to get an exact functional form for the entire entanglement dynamics. But we can also do it for any other kinds of defects, different other kind of point defects. Another thing that have been trying to do is to uh, try to understand how the hydrodynamics can be used in such kind of quantum setups. And we have been trying to use this kind of eigenvalue dynamics to get an understanding of it. Another, the thing that we have done in this paper is to get analytical expressions for full counting statistics. That is the distribution of number of particles that are there in the system at a given time. We, at least for the conformal defect, we were able to analytically get the exact probability distribution. And we have shown that the probability distribution takes some binomial form. And final thing that we have shown is we were able to get some analytical expression for the dynamics of number entropy. Like, okay, as we know that measuring entanglement entropy in an experimental setup is very difficult. It's very challenging. So instead of measuring that, we can work with something, some other quantity which can be which is experimentally tractable, but at the same time gives some idea about how entanglement evolves. And one of such quantity was number entropy, and we were able to show that, analytically show that number entropy grows logarithmically slower than the entanglement entropy, at least for the conformal defect case. And okay, I won't be going in details of any of this topic, but if anybody has some questions about it, please ask, and I'm free to discuss after the talk as well.
Thank you, sir.
So okay, anyways, I would just like to conclude that the evolution of eigenvalues have some promising direction in like understanding the dynamics of entanglement in such setups, in such class of problems, and it's a very interesting thing to look at. I'll also like to thank all my collaborators who are shown here. So thank you for your attention.
I have a simple question. What happens if you put bosons instead of fermions?
Bosons instead of bosons won't be that simple. I have not checked it, but first of all, you won't have some kind of Pauli's exclusion. So at a given site, you can have multiple bosons, right? So that might create some problems. I don't think you will get similar kind of evolution. I have not checked it, but you won't get something similar. I can't. I don't know.
You said that all the information about the entanglement can be obtained from the correlation metric.
Yeah.
Right. So, I mean, that's a closed form expression.
Yeah. You can, the eigenvalues of correlation metrics, they are like, say, von Neumann entropy. Von Neumann entropy just can be given as this thing. Plus 1 minus zeta m log 1 minus zeta.
Okay.
That is a closed form.
So then the reduced density matrix on the subsystem can also be related to the correlation.
Oh, I'm talking about reduced density matrix. Okay, sorry. When I meant reduced density matrix, sorry.
The subsystem can be related to the correlation matrix.
Yeah, it should be. It should be, because yeah, here I'm just talking about the correlation eigenvalues of the system part of the correlation matrix, which you can do. So I think you can, yeah.
Also, that plot where you showed that the eigenvalues,
Hmm.
so
Those are for the correlation
metric
metric.
of the system.
Yeah.
So is it possible that you must have a dynamical equation for how the eigenvalues follow this thing?
Dynamical equation of how
Because
eigenvalues.
you have like time data with time the eigenvalues. So
Yeah,
you must have a
right.
dynamical equation. How the
Yeah,
eigenvalues-
I have, yeah.
Then-
For conformal defect, I have it exactly. For any other defect, I can say that I can write a exact equation up till some time, but not for entire dynamics.
And so for then obviously for the entanglement.
Right. At least, yeah. If I have the equation, I can just put it in the computer. By hand, I can't do. Yeah. It's a little complicated. Okay, just one thing that it's a leading order. The result that you will get will be a leading order result because there are still some eigenvalues which are like between two levels, which are not taken into account, which will give some logarithmic correction to it. Which, yeah.
Maybe I missed one thing. Did you say that this evolution of eigenvalues does not depend on the form of coupling between system and reservoir?
No, it depends.
Okay,
It does not, for conformal defect, it does not depend on the momentum mode.
okay.
That's why we were getting the flat lines, like saturation, like constant values. If you have some other defect, say just like different hopping at the coupling site, then you will get some reflection coefficient which are dependent on the momentum modes. In that case, the eigenvalue distribution itself will have some momentum dependence. And since I'm not plotting it against the momentum value, it will have a complicated form. But even that we can probably get that form as well, the function of that form.
Hi, thanks. So I wanted to ask, you mentioned relation between this entanglement entropy and hydrodynamic entropy. So if you are doing hydrodynamics, what would your slow variables be in this case?
Sorry, what will be?
Hydrodynamics, there should be some slow variables.
No variables. I'm not sure. Okay. You can, the phase space density can be written like for a hydrodynamic theory, you can write the phase space density of the particles in terms of something called a Wigner functions, which is related to, again, the correlation metrics that you get here. So you can get the phase space density which satisfies the Euler equations.
So in this case, it seems there would be some relation between hydrodynamic entropy and entanglement entropy because you said the correlation matrix relates. But what if you, because you also mentioned that the correlation matrix has info about non-interacting systems.
This is a non-interacting system.
Yeah, so what if you do have an interaction?
In case of interactions, I'm not sure what will happen. Yeah, it gets a little complicated. Oh, okay, right. In case of interaction, the entanglement is not defined just by the correlation matrix. You need some higher order terms as well. Like 2-point correlation is not enough, I think. Yeah.
And how does that relate to hydrodynamic entropy?
I don't know. I have not checked that.
Thanks.
You said that this correlation matrix eigenvalues are used in transport properties as in reflection probability. How do I see that analytically?
Okay, there is a paper by Victor Essler and Pascal in 2012, I think, where they studied a similar setup but equipartitioned them, and they gave an analytical expression for that. They actually gave an analytical expression, but they only saw the evolution from 1 to first level. Since it's a equipartition system, they didn't get that thing. Yeah, but there is a way to get this thing.
Thank you, Atharva. Let's time this.